We're going to do part two of our applied optimization problem. So in the last video, we did problems 1, 2, and 3, and we talked about how you can do problem number 4. And in this video, we're going to look at problems 5 and 6. So 5 says an open box is to be made from a 16-inch by 30-inch piece of cardboard by cutting out squares of equal size from the four corners and bending up the sides. What size should the squares be to obtain a box with the largest possible volume? So here's a diagram of the situation. We have this 16 by 30-inch piece of cardboard, and we're going to cut out these squares from the four corners. And I've labeled the side lengths of each of these squares X, and they're squares of equal size. So we're going to cut out these squares, remove them, and notice what we'll end up having is a base with four flaps. Okay, and these flaps are going to bend up, and we're going to create a box out of this. So the box won't have a top, but you can see the base here in blue and the four flaps that will fold up or bend up in orange. Now notice also that we can adjust the size of X, and that will vary the size of the base and the flap. So for example, if I make X be really big, then we're going to have a small base here, but the flaps will be really tall. They'll be really big. So it'll be a tall box, but not much base. On the other hand, if we go the opposite direction, we let X be really small, we'll have a big base, but the flaps won't be very tall. In fact, if we go to an extreme and let X be 0, then we don't even really have a box anymore. We just have a base, and it's not going to have any volume because we're not going to have any flaps to bend up. Same thing if we go the exact opposite direction. If we let X be 8, notice the biggest possible value X can take is 8, because this is 16 right here. Then notice again, we don't really have a box because our base has completely disappeared. So X taking a value somewhere between 0 and 8 is going to give us a box with largest possible volume. So what is that value of X? What is that happy medium that will give us a box with the largest possible volume? You can see I actually did this one time. I took a piece of paper and I cut out squares from the four corners, and I made these different trays. And you can see, notice the different sizes and shapes of these trays. That just has to do with how big of squares I cut out from the corner. So I made a total of 5 different ones. And it turns out they don't all have the same volume, right? Different ones will have different volumes. And so the question is, how big should you cut out the squares from the four corners to make it have largest possible volume? So here's a hand-drawn version of this diagram. And again, we're going to let X denote the side length of each of these squares. Now, the volume of a box, of course, is length times width times height. But what are those dimensions? What is the length, width, and height of this box? Well, notice this length down here is 30, but that's not the length of our box. The length of our box is this length. Well, what is that length? Well, if this is X and this is X, shouldn't this be 30 minus 2X? And same thing here. If this big length here is 16, and this length is X, this length is X, this length should be 16 minus 2X. So the length is 30 minus 2X, the width is 16 minus 2X, and the height is just X. Now notice also that X has to be between 0 and 8, just like we mentioned before. Certainly X can't be less than 0, and also X can't be bigger than 8 because these squares would overlap each other right here because this is 16. So we're trying to maximize this volume function subject to the constraint that X is between 0 and 8. So what value of X would make this as big as possible if we're picking values of X between 0 and 8? So we will call this V of X, and we're going to have to FOIL this out. Now, minus 2X times minus 2X is 4X squared. We're going to have a minus 32X from the inside two terms and a minus 60X from the outside two terms. That's a minus 92X. And 16 times 30 is 480. Okay, so we FOILed that out. Now we're going to distribute the X. We have 4X cubed minus 92X squared plus 480X. So this is the function that we're trying to maximize, subject to the constraint that X is between 0 and 8. Okay, well, how do we maximize it? Well, we have to find the critical numbers, right? We're going to find V prime of X, and V prime of X is 12X squared minus 184X plus 480. Now, I have to say the next part of the problem is really the hardest part of this whole problem by far, and that is, how do you factor this? Well, one thing that you might notice is that all these coefficients are even, so we should be able to at least factor out a 2. In fact, all of them are at least divisible by 4. So let's factor out a 4. We have 4 times 3x squared minus 46x plus 120. Now, even at this point, this is quite difficult to factor. If you didn't know how to factor this, or maybe if this were not factorable at all, that would still be okay. What you would have to do is to use the quadratic formula, right? So remember the quadratic formula. So you could just plug in the coefficients here, and that will give you the x value. So if you can't factor something, you can always use the quadratic formula. But this one actually does factor, and the way that it factors is we're going to have a 3x and an x here to multiply to get 3x squared. It's actually 3x minus 10 and x minus 12. There's a lot of possibilities to try, so that's why it makes it so tricky to factor. But if you notice, negative 10 times negative 12 is positive 120. We have a negative 10x from the inside terms and a negative 36x from the outside, so that gives us negative 46, and 3x times x is 3x squared. So notice, what are the zeros? Well, this one gives us x equals 12 as a 0. What about this one? Well, we have 3x minus 10 equals 0. And if we solve that for x, we get 3x equals 10, or x equals 10 thirds. Now, remember, our x has to be between 0 and 8. So that actually rules out this possibility of x equals 12. So x equals 10 thirds, or 3 and 1/3, that's our only possibility. And in fact, that has to be the maximum, because v of 0 is going to be 0, and v of 8 will also be 0, right? Just from looking at the picture here, right? If the x is 0, the volume is going to be 0, and if x is 8, the volume is going to be 8. Or you could look at this formula. If you plug in 0 for x or 8 for x, you're going to get 0. So the squares we have to cut out have a side length of 10 thirds inches. Now, you might wonder what the volume actually is when we plug in 10 thirds. So find V of 10 thirds. And if you do that, you get V of 10 thirds equals, and you could use a calculator here, this would be about 725.9. Okay, and that would be cubic inches. That's the maximum volume that we could get from cutting out these squares, and that happens when we cut out the squares to be 3 and 1/3 inches, or 10 thirds inches. And here's actually a graph of that volume function here. Now, this is not foiled out here, but this is the volume function. And notice right here, 3 and 1/3, 3.3 repeating, gives us the largest possible volume, right? If we cut out squares of width 3, let's say, then we only get a volume of 720. If we cut out squares of width 4, then we get a volume of 704. Notice if we cut out squares of width 8, then you get a volume of 0. In fact, it's kind of weird. The formula actually becomes negative, and that actually doesn't even make sense to have a negative volume. But it's clear that our x's can't be any bigger than 8 that we're cutting out from the 4 corners. So actually, we can just ignore the rest of the graph over here and the graph over here as well. We're only looking at between 0 and 8. And there, the maximum occurs at 3 and 1/3, and the maximum itself is 725.9. So that's 3 and 1/3 inches, and that's 725.9 cubic inches. Okay, on to the last problem. A fence must be built to enclose a rectangular area of 4,860 square feet. Two opposite sides, the sides facing north and south, so these sides in red here, will use cheaper fencing costing $3 per foot. And the remaining two sides will use heavy-duty fencing, so these blue sides, costing $5 per foot. Find the dimensions and the cost of the least expensive fence. Now, our first thought might be, why don't we just do a square? Because of all possible rectangles that are going to enclose an area of 4,860 square feet, the one that's going to use the least amount of fencing would be a square. But remember, we're not trying to use the least amount of fencing. We're trying to find the least expensive fence. And the fact that these sides are so much more expensive here, the blue sides, means that we probably don't want to make these as long. We probably want to have the red sides longer than the blue sides. If we still want to enclose this large area, we probably want to have more of the red than the blue. Okay, I've defined some variables here. We're going to let x denote the length of the side of the rectangle that's using the cheaper fencing. And we're going to let y denote the length of the side of the rectangle that's using the more expensive fencing. And remember that the thing that we're trying to minimize is the cost. So what is the total cost to build this fence? Well, the cost is going to be the cost to build, first of all, this side. Well, how much does this side cost? Well, if this is x feet long and it costs $3 per foot, it's going to cost 3x. Okay, for example, if this was 100 feet long, well, if it costs $3 a foot, it's going to cost $300. And same thing over here. If this is x feet long and it costs $3 a foot, this will cost 3x. Now this side will cost 5y and this side will cost 5y. So notice that the total cost is going to be 6x plus 10y. Now we have two variables here, x and y, and I'd like to get rid of one of those variables. So how do we do that? Well, notice we haven't yet used the fact that we want the total area to be 4,860 square feet. And remember that the area is the length times the width, right? The area of a rectangle. So we have x times y equals 4,860. Well, notice this gives us a relationship between x and y, because if we divide both sides by x, let's say, we get y equals 4,860 over x. And we can actually plug that value in for y here. So the cost is going to be 6x plus 10y, but y was 4,860 divided by x. And so we have this is equal to 6x plus, well, if we multiply by 10, we're going to get 48,600 divided by x. And we'll call this c of x. Okay, so we're trying to minimize the cost function. Now, one constraint that we clearly have is that we don't want x to be negative, right? So x certainly has to be greater than or equal to 0. So how do we find the value of x that's going to minimize this? Well, we need to take the derivative. And how do we take the derivative of this? Well, it's going to be easiest if we rewrite this second term as 48,600 times x to the minus 1. You could take the derivative using the quotient rule, low d high minus high d low all over low squared, but I think it's just easier to do it this way. Okay, so what is c prime of x? Well, c prime of x is 6 minus, right, we're bringing the minus 1 out front, 48,600 times x to the negative 2. Or put another way, it's 6 minus 48,600 over x squared. Now, we don't have a polynomial here, so we can't really factor this here, but we're trying to find the value of x that's going to make this equal to 0. So let's actually set it equal to 0 and solve for x. Okay, we've set it equal to 0. Now we're going to add this term to both sides, and we're going to get 6 equals 48,600 over x squared. And then we'll multiply both sides by x squared, and we get 6x squared equals 48,600. Then we divide both sides by 6, and we're going to get x squared equals 48,600 divided by 6. Now, if I were just randomly making up numbers, this number probably wouldn't be divisible by 6, but I think it is divisible by 6. And so I rigged this up to give us a nice number. In fact, I believe this is 8,100. In fact, I really rigged this up because x squared is 8,100. So you'd expect x maybe to be some crazy decimal, but actually it's actually 90 squared that equals 8,100. So x is going to be the square root of 8,100. So x is 90. So what does that mean? Is that $90? 90 what? Well, that's 90 feet. So 90 is our critical number. Well, if x is 90, what's y? Well, here we have to go back to this, right? We have x times y has to equal 4,860. So if x is 90, what will y be? And it turns out if you work this out, you get 54. And that's 54 feet. And this actually makes a lot of sense because the y should not be as long, 54 feet, as the x, right? Because that's the more expensive fencing, and this is the cheaper fencing. Now, what would the actual total cost be to build this? Well, we could go to our cost function here and do really take any one of these formulas here for c of x, any one of these. Maybe this one's the easiest to use, and just plug in 90 for x and 54 for y. And if you do that, you get 1,080. So that's $1,080. So the dimensions that give you the least expensive fence are 90 right here and 54 here. And the total cost is 1,080. Now, I do actually have a graph here in Desmos for c of x. Now, remember, this was really the 10y, 6x plus 10y, but I wanted to keep it as a single variable here. So the x-axis here denotes the x in the previous one, and the y-axis here denotes the cost. So notice this point here is 90, 1,080. So when we let the x be 90, the cost was 1,080. If we varied that a little bit, though, we let the x be something different, notice the cost is higher. Okay, or if I let the x be, say, 40 feet, well, then the cost is $1,455, right? It's more expensive. The least expensive fence is when the x was 90.